This is a quick review of integration from Calculus 1. We can think of the basic integration problem as being a problem about area. And the simplest version of this is the area between a curve and the x-axis over an interval, as we see here. So in this case, the question is, what is the area of the gray region shown? That is the region below y equals square root of x and the x-axis between x equals 1 and x equals 4. The first thing we did in Calculus 1 was get an estimate of the answer to this. We can do that by breaking the region into strips and then estimating the answer to each of the strips. So in this case, if we were to break the region on the left into 6 equally wide strips, by just cutting it straight down this way into 6 pieces, then each one of those strips could be estimated, or the area of each of those strips could be estimated by using a rectangle instead of the actual strip itself, and we would get an answer that's pretty close. The area of a rectangle, of course, is easy geometrically. It's just the height of the rectangle times the width, and if we've split this evenly, then each of the widths of these strips will be the same, in this case 0.5. The height of the strips is just the height of the rectangle, and the height of the rectangle is the y-coordinate on the curve at a particular point. And so we call these the left rectangles because the top of the rectangle touches the curve on its left-hand side. So this rectangle's height is the y-coordinate here. Well, that's the y-coordinate of the curve y equals square root of x over the point, or over the number x equals 1, and that's why we get square root of 1. The height of the point here, the height of the rectangle here is the y-coordinate of this point, which is the square root of 1.5. Square root of 2, square root of 2.5, square root of 3, square root of 3.5. And so each of those areas are just a height times width, and we add them all together and get 4.41. A couple of things about this. First of all, we can tell that the sum of the areas of these rectangles is going to be less than the actual area of the gray part, because each of the rectangles falls underneath the curve. And so you can see we've wasted a little bit of space, which you can see in between the rectangles and the curve. So I know that this answer I'm getting is actually less than it should be. So the real answer is a little bigger than 4.41. The other thing to talk about is the notation that we can use for this. Each of these values are coming from the function f at a certain value. So that was f of 1. This is f of 1.5, and so on. So because those heights are coming from y-coordinates on the curve, that means they're always f of something. And of course the widths are always the same. And so you can see that we can use sigma notation to capture the fact that the height is always f of something. So those are the heights, and they're f of something because they're y-coordinates on the curve. And then the width is represented by delta x, which is supposed to represent a change in x, and of course this is the x-axis, so this is the x direction. So a change this way would be considered a change in x. The reason for pointing this out is that this looks a lot like our definite integral notation that we'll see later on. It's a sum of a y-coordinate times a width. Another way we could have approximated the strips would have been to use rectangles that overlap the strips, as we see here. We would consider these right rectangles because the top of the rectangle is touching the curve on the right-hand side in each of these cases. So square root of 1.5, square root of 2, and so on up to the square root of 4, which is 2. The widths of these are still 0.5, and so we still have the same basic kind of expression, just with slightly different y-coordinates used for the rectangles. But the summation notation will look very similar. These values of x now are just the places where, just the values of x below where the rectangle touches the curve. But we can still see how that's suggestive of the integral notation that we'll talk about later. And so we can get a bound on our area problem by just looking at these two different kinds of rectangles. The left rectangles are too small, the right rectangles are too big. And so we know that the correct area is somewhere in between those two estimates, in this case between 4.41 and 4.91. There's nothing special about 6, of course, so if we use more rectangles, what we'll see is the values get closer together. So here's a screenshot of what it would look like to have 30 left rectangles and 30 right rectangles. Again, the left rectangles are too small, the right rectangles are too big, and so we know the real area is in between. But now the two estimates are a lot closer together. 4.62 and 4.72 is really narrowing down what our value of A is. And so when I stop at 30, we could also do 300 rectangles. I'm not showing you a picture of that because it's hard to tell what you're doing with that many rectangles. And certainly 3,000 rectangles would be a huge number. But notice that with 3,000 rectangles, our two estimates are 4.666 and 4.667. And so those estimates give us a really good idea of what the actual area is. But that's computationally difficult. To calculate 3,000 rectangles and add up their areas is extremely tedious, and the fundamental theory of calculus allows us to get around that. The fundamental theory of calculus says that the exact area, which we will denote this way, the exact area, and you can see how this harkens to y-coordinate times width of these strips that we've been talking about. So the notation is very, very similar to the sigma notation. This comes from the exact calculation would be to calculate capital F of 4 and subtract capital F of 1. And the caveat is capital F of x is an antiderivative of little f of x, meaning that capital F of x's derivative is just little f of x. So being able to use the fundamental theorem of calculus in this way requires that we're able to figure out a capital F function whose derivative is the integrand that we've been looking at. So in this problem, that's not too hard. I've done the calculation here. The derivative of 2/3 x to the 3/2 is just x to the 1/2, which is square root of x. And so this is a function. This is the capital F of x for this problem. It's one possibility for capital F of x. The fundamental theorem of calculus doesn't care which antiderivative you use. But in this case, capital F of x being 2/3 x to the 3/2 has the correct property. The derivative of that capital F is square root of x. And so to calculate this integral, we just take the value of, the formula for the antiderivative that we identified, and we evaluated at 4, and we evaluated at 1, and we subtract. So here's the antiderivative evaluated at 4, as we've written here. Here's the antiderivative evaluated at 1, as we've written there. And of course, I'm just subtracting the 2. And so this gives us 16/3 minus 2/3, which is 14/3. And you won't be surprised to find out that 14/3 is exactly 4.66666 repeating, which is what our estimates suggested was going to happen. That's the basic idea. A lot of what we do in Calculus 2 is going to be, first of all, thinking about other ways to approximate this problem rather than rectangles. We will also talk a lot about how do you figure out what this capital F should be in order to be able to use the fundamental theorem of calculus, and we'll talk about those things from lots of different points of view.